My name is Charles Parker, and I'm the VP of Machine Learning Algorithms here at BigML. And I know we usually use this space, these quarterly releases, to kind of showcase some very new type of model or new type of data analysis you can do. But we're going to focus on this release on functionality we've added to the platform that makes it easier to use the models that you've already trained and models that you already can train on BigML. So first of all, what does it take to actually use a model? So let's say you've trained this very nice supervised machine learning model. You've got a model that's able to make predictions for you. That's great. One of the things I like to say about machine learning, though, is it's a hammer. So it's a tool that has a specific use. And if you don't know how to use it, if you're using your hammer to pound in screws, then it's going to fail for you. So it's important that we use this model properly. So what do we want to use this model for? Well, one thing we can use it for is to make predictions, just like I said a second ago. And so let's think about that. What are we going to make predictions about? And then once we've made the prediction, we get a prediction from our machine learning model. What happens afterwards? So what happens when you have the model's prediction? What are you going to do with that? And one of the answers to this question is that you probably need an operating threshold. You probably have to have some idea of how to interpret that model's predictions. And then the other thing you might want to do with a machine learning model once you've trained it is to share it. And so the question that immediately arises is, who are you going to share this model with? And a way of talking about how you want to share these models and who you want to see these models that you've trained is BigML's new organizations feature. So those are the two features we're going to talk about in this release, are operating thresholds and organizations. Machine learning has many dirty little secrets, but one of the big ones is that once you train a supervised learning model, it still has no idea what you want. And this is kind of an open secret in the machine learning community, is that you train a supervised learning model, and then there always needs to be some logic that interprets its predictions or filters its predictions somehow on top of the machine learning model's predictions itself. And the reason for this is that when the model trains, when the model learns itself, it's optimizing its own version of loss when the algorithm learns a model from your data. And what that means is the model's just going to try to get as good of an accuracy number as it can on the data set you've given it, on the training data set you've given it, without any regard to the semantics of the data. So it doesn't know if one type of mistake is really bad and another type of mistake is really good. It's going to treat all mistakes equally. It's going to say, okay, making a mistake is bad. Doesn't matter what kind of mistake it is. I'm just going to try to minimize the number of mistakes I'm making. So that's what we mean by we say the model's optimizing its own version of loss. It has a set of assumptions that it's working with about your data, and those assumptions are fairly naive. And so there are some ways to kind of impart a little bit of knowledge about your values to the learning process. So before learning begins, you can say certain things to the model. Like, for example, you can say, okay, I know I only have a few instances of this class over here, but I want you to treat those instances as a group as being just as important as this huge group of instances over here, even though there's more of them. So this is what we have the balance objective pull down for in model training. That's what this does, is it tells you to treat the classes as being balanced. And so that's one way you can tell your model that, hey, you know, even though there's way less of this class, it's just as important as this other class over here. And similarly, if you want to get more fine-grained about it, you can add a weight column, which allows you to specify a numeric weight for each instance in your data set, which is basically saying, hey, work harder to get this instance right. You can work less hard to get this instance right, depending on what the value of the weight is for that instance. So that's good, but that kind of requires you to do this elaborate setup beforehand, right? You have to either specify weights, or you have to know you have a problem where you want the objective balanced. A lot of times you can apply these sorts of preferences after you're done learning, but of course you can only apply these preferences if you know what they are. And so we can discover the preferences we have around these models' predictions using an evaluation. Now, I know all this sounds very kind of amorphous and theoretical right now, but we're definitely going to get into a few examples here if you just sit tight for a moment. And so this is what the evaluation looks like, the evaluation visualization on the BigML platform. And one important thing is we have evaluation curves. So up here, by default, we show you the confusion matrix at for this model at the given default probability threshold. And if you select one of these other buttons here, we show you a curve that summarizes the model's performance. And what we see here, the first curve in this list of curves is the ROC curve, which basically tells you for each possible probability threshold in the model, what the false positive rate is and what the true positive rate is. And the deal is that we can change for a given class. So we select a class we want. So in this case, we're going to select a good class, whatever that happens to mean for this data. And we can slide around this little probability threshold slider, and we can change the confusion matrix. We can move the threshold around on that plot we see below, which will change the confusion matrix. And basically, the idea is that when we lower this probability threshold, we're going to be more aggressive in predicting the class that we have labeled as the positive class up there. So if we lower the probability threshold, that means, hey, if the probability threshold is 20%, the model only has to think it's 20% likely before it predicts the positive class being good, rather than the default 50%. So this threshold slider is kind of the key mechanism we can use to discover how aggressive we want our model to be in predicting some class. So basically, we move that threshold slider around, and if the probability of the class that you have labeled as the positive class up there, if the probability is over the threshold you've selected, then BigML predicts it. And if the probability is not, then we're just going to select the next highest probability other class, other than the positive class. So this is a really neat mechanism, right? If we slide that slider all the way down to 0, then that means the model's going to predict everything positively. Everything is going to be the positive class because there's no probability that the model will predict less than 0. And if we slide it all the way to the top at 100%, the model's not going to predict anything to be that positive class because there's no probability that the model is going to predict greater than 100%. And then in between, we have this universe of possibilities, right? We have all these possibilities where you might predict a lot of things positively or just a few. And you can select that, move that around as you like. So why might you want to do this? Why might you want to move that probability threshold around and be more aggressive or less aggressive in predicting some class? I'm going to go through 4 cases here. And one of the most obvious and kind of the most intuitive one to grasp is medical diagnosis. So suppose you have the cost of false positives and false negatives being very different. This is the case in medical diagnosis, right? Because the positive class is very rare. And so the model probably won't predict it very often because, again, the model is trying to optimize its number of mistakes. If one class almost never happens, making a mistake on that class is not going to happen very often either. And so the model is going to probably ignore a lot of that small number of mistakes in favor of getting its answer right on the larger class, the class with more members, which would be the negative class in this case. Most people don't have some disease, right? Unfortunately, that's the opposite of what you want. What you want is a model that predicts the positive class whenever it happens. The positive class in this case is more important than the negative class, the people who don't have the disease. Why is that? Well, if you think about it, the people who have the disease, if you make a mistake on one of those people, if you miss them, if you send them home and say, no, you don't have this disease, the consequences are pretty dramatic, right? If it's, say, diabetes, like the data set we're going to see in a moment, if it's diabetes, then you send the person home, maybe they go into insulin shock, maybe they have to have more treatment further down the road for various complications related to diabetes. So you want to catch them early. You want to make sure that they get the insulin they need in their bloodstream so that they don't encounter any more adverse health effects. On the other hand, let's think about making a mistake on the other group of people. So if you don't have diabetes and the doctor says, yes, we think you have diabetes, the consequences aren't so dramatic, right? The consequences are maybe you have to monitor your blood sugar for a little while, and then finally you find out that you don't have diabetes. That's not so bad, right? You just had to do some monitoring, but there were no adverse health consequences from you accidentally being diagnosed as a false positive for this particular disease. So in this case, we really want to get right those people who have diabetes. We really want to make sure those people are classified correctly. And the other class of people, again, we don't want a false positive, but we're more willing to put up with those false positive diagnoses. You can use the evaluation to kind of set the trade-off between the types of error. So if I go over here, here's an evaluation I did on my diabetes diagnosis data set earlier today. And again, we've split the entire data set into a training set that has 80% of the instances and a test set that has 20%. And we've done our evaluation on this held out data, which is very important. And you can read about that all over the internet, why you have to split up your training and test data to get an accurate evaluation. And so I've done that in this case, and then here's the results of the evaluation. You can see I've selected the ROC curve to view here, and I've selected my positive class as being true, the people who have diabetes. And now, right now, I've got the probability threshold at 50%, which is the default. And you can see here, I'm predicting true for 40 people. I'm predicting false for 114 people in the data set. That's probably about right, because not too many people have diabetes compared to the general population. Most people don't have diabetes. But you can see that this gives me a trade-off that's probably not acceptable, right? I'm only introducing 7 false positives here. So I'm only saying that 7 people out of the population of people without diabetes, which is 93 here, only 7 of those I'm predicting have diabetes, which is good. That's a very low false positive rate. But look at this. I'm missing 28 people who have diabetes out of 61. I'm missing nearly half the people who have diabetes with this model under the default behavior. That's probably not good, right? That's probably not the trade-off we want to make, where we get 4 times as many false negatives as false positives. As I said, false negatives have the more dramatic consequence here. So the solution to this is we want to be more aggressive when we predict whether a person has diabetes or not. And so we're more aggressive by dropping this threshold down, which again is saying, okay, if the probability of this class here true is over this threshold, then I'm going to predict it. And I want to lower that threshold. I want to make that happen more often. I want to diagnose more people with diabetes. And so as I drag this down, you can see that this number gets very low, right? Now I'm only missing 10% of the people who have diabetes. That's much better, right? I'm picking up more than 90% of them. On the other hand, if you look down here, I've introduced all these false positives, right? Again, maybe that's okay in this case, right? Right now, I've got 40 false positives or 40-ish false positives. I've got 5 false negatives. That might be the trade-off we want to make. We might think to ourselves, oh yeah, it's worth giving 8 people a false positive diagnosis in order to avoid missing a true diagnosis for 1 person, because that's about the ratio of mistakes we're making here, right? 8 to 1. Sometimes in a lot of these domains, it's hard to quantify exactly what false positives and false negatives are worth, and that's the trade-off you're making here. And so basically you can slide this threshold around until you find a trade-off that kind of meets the eye test, until you find a trade-off that's like, okay, you know, I can live with that. I can live with that number of false positives and false negatives. As I said there a second ago, sometimes it's hard to assign an actual dollar cost to our false positives and false negatives. But sometimes it's not, right? Sometimes you know precisely the cost of making a classification that has a certain outcome. And this is kind of a subset of the case that I just discussed. So we were sliding that slider around there, and we were trying to find a good trade-off between false positives and false negatives. But sometimes it's not so nuanced as that. It's not so nuanced as looking at that confusion matrix and thinking, okay, I can live with this. Sometimes you know exactly these costs. So let's say you're predicting failure for a big, like, industrial type of machine. And if your model predicts that the machine is about to fail, you want to send a tech out there to do some repair work on it. So in this case, every time you predict positively, you have to pay the cost of sending the tech out into the field. That is some cost. Now, if you miss something, if you don't label, yes, the machine is going to fail, and it fails anyway, then you have to pay the cost of the downtime, and you have to send the tech anyway. So that's going to cost more than the tech by itself, right? There's some cost to that downtime that the machine experiences if you miss the failure. And then finally, true negatives cost nothing. So if you predict that the machine's not going to fail and it doesn't fail, you don't send the tech into the field, there's no downtime, you experience no added cost. And so when you have these costs, one thing you can do is you can move that slider around a whole bunch and get out your calculator and, you know, add up the costs for each quadrant in that confusion matrix, and then find the minimum threshold based on all that computation that you've done. Or you can use WhizzML, which is our domain-specific language for the BigML platform. And you can use WhizzML to find the optimal threshold given the cost that you have. So I've got an example of that right here. This is a short WhizzML script that I've written. And if you can look at the code for it here, it's not very long. There's only, what do we got? 40 lines of WhizzML. And basically, you don't have to go into the details of this script. We have a related script on one of our blog posts. Or if you're interested in having this script, you can always email support@bigml.com and we can give it to you. But the basic idea here is that I've got an evaluation that I've created, and I've got a class that I'm going to say is the positive class. And then I've got these costs, false positives, false negatives, true positives, true negatives, for each possible outcome when I make a classification. And like I said, if I know those costs, it's easy for me to go through every evaluation, look at every possible threshold, look at the confusion matrix for that threshold, apply these costs, and see if I can find the minimum cost threshold. And so here, if I go to my diabetes diagnosis evaluation, here, I'm applying these costs. In the example in the slides, I'm using failure of a machine, but you can apply this generally to any situation where you know these false positives and false negative costs. So here's the diabetes evaluation, and I'm applying 2 for the cost of a false positive. You have to walk around for a while, monitor your blood sugar, and then I'm applying 10 for a cost of false negative. It's much worse, right? You experience some adverse health effects. Maybe you have to go to the emergency room and so on and so forth. So this, not as bad as this. And so if I execute this script, it's just going to go through all of the possible thresholds in that evaluation, and it's going to tell me what the optimal threshold is for that, given those costs. And so here, you see exactly that. Here it's saying that the optimal threshold is 18%, given those costs, and then the lowest cost that it found is 98. And so this is pretty slick, right? Because depending on, if you do a new evaluation or if your costs change somehow, you can always reevaluate the script and get these 2 numbers out very quickly. So that's kind of the beauty of WhizzML, is once you have the script set up, you can do something over and over again, and there's no friction. You don't have to, redo that. If you have new costs, you don't have to redo that work with the slider where you're sliding it around to every threshold and looking for the minimum threshold. Here, it's 1 click basically, and you're done. Note that the threshold here is much less than 50%. Why? Because we assign the cost of a false negative to be very high again. So of course, it's going to lower that threshold to be more aggressive in predicting the positive class. And this is such a useful idea, the idea of being able to directly specify these costs, that we're probably going to bring it to the interface, the evaluation interface very soon. So please stay on the lookout for that. Okay, case number 2 is going to be churn prediction. So the idea here with churn prediction is that you've got a subscription service. At the end of each month, some customers may leave. They may decide not to renew their subscription, and you want to take some action to retain them. So you want to predict which customers are going to leave and which are not, and you want to reach out to those customers that you think are going to leave and say, hey, please don't leave the service, offer them a promotion or some discount, basically try to get them to stay with the service. And so in this case, maybe we don't know the exact costs of false positives and false negatives in this case. This is kind of a tricky case because you don't know in advance. It's hard to know in advance how successful your retention effort is going to be. So, you can say, oh, it costs nothing when I identify one of these customers, but they might still leave the service. So it might cost you something even when you identify them. Another way to look at this problem is that you have a constraint on the number of times you can apply a class. So for example, in churn prediction, you want to call all these people that you identify as being likely to leave the service. That costs money, right? That you have to pay operators to make these phone calls. You have to pay money for the phones. You only have so much time to call people, given the number of operators that you have. So you have all these costs that are basically fixed in the domain. Unless you buy more operators or suddenly get more money to pay for this effort, you basically have a budget here of people you can call and you get to spend it. And you want to spend that budget calling as many people, calling the people that you think are most likely to leave the service. So the solution here is to set the threshold according to your budget and to use the evaluation tool to estimate the performance at that threshold. And so I'll go back to my data here. And you see I have another evaluation here, this telecom churn data. So this is exactly the sort of problem that we're talking about. And I'm going to select my positive class as being true, the people who are going to churn. And you can see here that I'm already doing pretty well on this problem here. I've got kind of 90-ish% accuracy overall. And here's the people I predict true. I predict 34 people out of 667 in the test data set will churn, and I'm right about 25 of them. So that's quite a lot of people that I'm right about. But this number might not be the right number for your company or your organization, because why? So I'm predicting 34 people are going to churn. I've got 667 people. That's about 10% I'm predicting are going to churn. What if you have millions of customers or tens of millions of customers? You only, that means you're going to be calling what? Like hundreds of thousands of people each month. Unless you have the staff or the budget to do that, that might not be the right threshold for you. Maybe you only have enough resources to contact, say, 2 people or 2% of your subscribers each month. And so what you want to do is you want to get the 2% that are most likely to churn, and you want to use your resources to contact that 2% of people. And so a way to do this is to move the probability threshold slider around until this number you're predicting true goes down to 2% of your whole data set, which is what, 12 or 13. So let's be less aggressive in predicting this class, less aggressive. Now I'm at 13. So I've moved all this probability slider all the way to 71%, which means the model, the probability of the class, the churn class has to be over 70% before the model will predict it. So the bar is pretty high now. And as you can see, now I'm only predicting 13 people are going to churn. And so that's a little more in line with what I wanted, right? I can only afford to call 2% of my total subscription base. And so 13% is in line with that. But also you'll notice that this number is better, right? At 50%, I'm getting a sort of 70-ish% success rate when I call somebody. So basically 70% of those people that I call are going to leave the service. When I move the threshold up to 71, like I had it before, now I'm getting a much higher success rate. So basically I'm taking the cream of the crop essentially. So I'm not just taking some random 2% out of that 5% that I was labeling positive. I'm taking the 2% that I think are the most likely, right? That's the beauty of these thresholds, is regardless of where you move them around, they'll always take the best fraction of the ones that are allowed to predict positively. So I fixed my problem, right? Now I'm only calling 2% of my subscriber base. I'm calling the 2% of the subscriber base that's most likely to churn according to the model, and I'm happy with that. And then a subset of this case comes when you've got a fixed constraint of the domain, like the churn case. You've got, kind of a 2% constraint, the number of people you want to call. But sometimes the input domain changes underneath you. So a good example of this is if you're a loan processor, you want to fund loans based on applications that come in. But let's say you have a funding situation such that you can only approve half of the loans that come in. So you've only got so much money to lend out, and given the application volume that you get and the amount of the loans that are being asked for, let's say you can only fund half of the loans that come in, half of the applications. And I have some loan application data right up here. And so again, if I move the slider over to 50%, the default threshold, you can see that I'm predicting 157 out of 250 people are good risks, that they'll probably pay back their loan. That's probably true, right? More people will pay back their loan than not in general. You don't get default rates of 50% on most credit problems in the real world. Unfortunately, that doesn't mean anything for my particular business, right? Just because I think this many people are going to succeed in general doesn't mean that I can loan money to all those people. Like I said, I can only loan money to half of the loans that come in. So that means raising this threshold until I get to 100 here out of the 200 total. And that's pretty close. And so there we go. Now I've set this much higher bar for acceptance. I'm only accepting half of the loans that come in, and so I'm happy. However, what happens if I suddenly start getting twice as many applications? So if I get twice as many applications, that means that same threshold, if I'm getting the same sort of applications, I'll be accepting twice as many loans, right? The data underneath me has changed. The data that's coming at me is different in volume from the way it was before. So the nice thing about this little threshold slider is I can use that same evaluation and just select a new threshold that will be even less aggressive in predicting the positive class, so that I accept even less loans by percentage than I was before. So if I'm getting twice as many loan applications, then that means I want to accept half as many loans that I am now to remain at a constant absolute number of loan acceptances, which means, again, raising this threshold until I'm down to 50%, or I'm down to 50 loans on this in this number here. So if I raise, you'll notice here the precision is 85%, so I've got a 15% default rate on the loans that I'm accepting. And so if I raise this number so that it goes up down to 50 here, now I'm only accepting a quarter of these loans, which is fine because I'm getting twice as many applications in. And now my default rate is down to 12%. So again, I'm able to accept less loans, but I'm also able to be pickier, right? I'm able to just choose the cream of the crop from among those loan applications I'm getting in. And so even though I can't accept any more loans, I'm still getting a better default rate just from increasing my data volume, because the amount of loan applications that are coming in allows me to be a bit pickier about who I accept and who I don't. Okay, so now what? Now I have this threshold. What do you do? Fortunately, once you've determined what your probability threshold is using the evaluation tool, BigML makes using the threshold awfully easy. Basically, there's always a button or a slider to use in the prediction interfaces for prediction and batch prediction, or if you're using WhizzML or the API, there's a parameter you can send that allows you to set that threshold. Moreover, if you are using one of the models that has support for confidence, which is basically depending on the instance you get, the model might be more or less confident in its predictions based on essentially the amount of data that you have that looks like the point that you got. So if the model supports confidence, you can threshold based on that as well. Here I have a prediction form. This is that diabetes diagnosis data. In this case, I've learned a ensemble of decision trees. And so I can threshold based on probability, or based on confidence, or based on the number of raw votes in the threshold, or in the ensemble. And so here you see that 7 of the 10 trees in the ensemble think that this person does not have diabetes. 3 think that this person does have diabetes. If I go to confidence, it's a little more circumspect. Both of those probabilities go down. And if I go to probability, then I get more exact versions of the probabilities given in votes, which is what happens typically. And then so the money here, the outcome of all this is that if I put my confidence here, we're 60%, or we're 23% confident that this person does not have diabetes. If I lower that threshold, you can see that right now I'm predicting diabetes is false. If I lower the confidence threshold down to 20%, then the model starts thinking, oh, this person wants to be more aggressive in predicting diabetes. So when it goes below this threshold, I'm going to change my overall prediction to true, even though we're only at 23% confidence. So that's what this confidence slider allows you to do. Again, is just be more aggressive in predicting a given class. In this case, diabetes is true. So that was the first topic we wanted to talk about today, was being able to set those thresholds to kind of tell your model what the various cost of mistakes it could possibly make are, to explicitly trade off between the types of mistakes it might make. The other thing we're going to talk about today is the new organizations feature. So as you might know, if you've spent some time in machine learning, it often involves a lot of duplicated work. What sort of work am I talking about? Well, pre-processing data, for one. You get a raw data set in. Usually it needs some work to make it machine learning ready, and you don't want to be doing that work over and over again. If you have a system where you're updating the models that are in production every so often, you don't want to have to, if you have that model being used in several different places in your company, for example, you don't want to have to push the data out to all those places and have them retrain the model every time it needs retraining. You'd like that all to happen automatically. And so it's silly, if you're part of the same organization or working group or company, it's silly to have this work duplicated, right? You should just be able to share these resources that you're creating, the pre-processed data sets, the models that are constantly being updated, and you should be able to just automatically have everyone in your organization have those, especially if you know ahead of time that these are the people who are going to want this thing. And so organizations is a fix for this problem. Basically, you're going to create an organization. This is how you do it in the interface. Organizations are separate from the user's individual account, so they have all separate resources. If you want to play around in your own individual account, that's fine. Nobody from the organization will be able to see it. And then once you have created an organization, you can invite other users to the organization. So let's see what that looks like real quick. And so here you can see this is my user, Charles L. Parker, and I'm in my personal account. And so if I go to new organization, I get this subscription form where I can sign up a new organization. I can add how many people do I want in the organization. I can have a subscription level that basically controls the size of things you're able to do in that organization, the size of data sets and models you're able to create, how fast you're able to create them. And then once you have that organization, if I go back to my user here, once you have that organization set up, this is an organization that I've already created called Parker BigML. You can go to organization settings and you can add users to the organization. So here I've added this guy Jones to the organization, and I can invite 4 more people. If I invite somebody, I can give their username here, and I can also give them a level of membership in the organization. What does that mean, a level of membership? Let's take a look. So users in the organization all have different roles. You can be the owner, which means you can do everything. You can be the admin, which allows you to do everything outside of basically managing the subscription level and deleting the organization. You can be a member, which allows you to create new projects in the organization, but not do really anything else at the organization level. Or you can be a restricted member, which allows you to only use the projects that you have permission to use. So again, it's nice to have people who are, trusted, able to really work with everything in the organization, or you can just give people some kind of limited access to the organization. And so that's what you see here. When you add an organization member, you add them at some level of permissions. We call these roles in the organization: owner, admin member, restricted member. Now, if I go back here, you can see that I've opened up a project in the organization. All resources in an organization have to belong to some project. And once you have a project in the organization, you can assign individual permissions for that project. So each project has per user settings that says, okay, this user can look at the resources in this project, they can create new resources, et cetera. And then the organization can have a whole bunch of projects. So depending on, working groups or teams around various topics that you have, you can always start a new project and say, okay, I only want these people to be able to access that project. So I've got this project. If I go to the settings for the project, edit current project, here's where I can set the project name and the tags or the description. I can also make it public, meaning all of the users in the organization can see it. That's not, the public at large. That's just public within your organization. And then also, if I go to view all projects, you can see down here that this is where I would set the permissions for the given project. So if I go to add here, if I select a user here, I select Jones, and then he has some level of permissions. So he can either have read permissions, which means he can only see the things in this project. He can't do anything with them or to them or create new resources. He has write permissions, which means he can create new resources or modify the ones that are already there. And then manage permissions, that means he can, not only can he view and create resources in the project, but he can also invite new users to the project if he wants to. So he can set the permissions levels for other users. So again, this is something that's very useful if you have a big group of people all working on related machine learning projects. You have things that you suspect you'd like to push out to other teams in the world, or to other parts of the company that you work for. You want to be able to train these models and then give them to people who will then do other things with them that you're not responsible for. If you have a data science team and they're training models for a given group, this makes it seamless to kind of add that group so that they can read the project where those resources were created, and then they can just pull them down as they want to. And if you retrain those models, of course, they'll immediately have access to the retrained models. So that's it for the webinar for today. As usual, we have a blog post, a series of blog posts leading up to this webinar, in which you can read more about creating operating thresholds, how you find them, how you use them in WhizzML and the API and the interface. A few more use cases that I didn't talk too much about here, and also organizations. We have our dashboard documentation, which enables you to, or which will let you read a little more about how they work on BigML. And then also we have a blog post about those as well that just came out a day or two ago.